Today we're going to be talking about graphing rational functions. So a rational function is a function in the form p of x over q of x. So you have possibility of an x value on top and the possibility of an x value on the bottom. And it can also be written in this other form. And this is going to be the main form we're looking at when we're graphing them, but just know that they can also look like this. So we're going to have a number over x plus or minus something plus k. And you might notice that this looks very similar. It's the same letters that we used when we do any other graphing, which means we can look at this with transformations. It's just not the way I'm going to approach this lesson. But just know that this a value would be the stretch or the shrink, right? If it was negative, that would be a reflection. The h is how we're moving left and right? And the k is how we're moving up and down. An asymptote is a line that a curve approaches as it heads towards infinity. And when we say approaches, we mean gets close to, but never crosses. So asymptotes will look something like this on a graph. So if you have your x and y axes, you have something like an asymptote here. So it's an invisible line that appears on the graph so that your graph's going to get really close to it and then never touch it ever again, right? It's never going to go through. And then maybe you have another asymptote here. So now our graph gets really close and never crosses, right? It's getting really close to both. And this is actually what our rational functions are going to look like. This shape is called a hyperbola. So we are going to be graphing hyperbolas. The vertical asymptote, the up and down line that we would draw, the imaginary line, is the h value, right? So x minus whatever that is, that number is our vertical asymptote. The horizontal asymptote is going to be the k value. It's possible that it's equal to 0 for either of these, right? If it's just an x on the bottom, x would equal 0. If it was just nothing, not adding or subtracting anything, y would equal 0. The domain is going to be all real numbers except where the asymptote was, because that's an invisible line that our graph won't cross, which means it will not be a number we plug in. So except for h, which means we can write our domain in interval form by saying from negative infinity up to h, not including h, right? Not bracket, it's a parenthesis, and from h to the rest of infinity. So we're basically just putting that h term, what's not allowed, in the middle. So we're saying everything up to h and everything past h, we're just not including h. And then the same idea for the range. The range is all real numbers except where our horizontal asymptote is, except for k. So that means we could write it as negative infinity to k and k to infinity. So the steps for graphing rational asymptotes. First, we're going to determine and sketch, rational functions. First, we'll determine and sketch the asymptotes. Then we're going to graph at least 3 points to the left and right of the vertical asymptote. So that means if your vertical asymptote was 2, we would plot 3, 4, and 5, right? Those are 3 to the right. And we could plot 1, 0, and negative 1, because those are 3 to the left. And then we could use additional information like x and y intercepts to assist us. And then we're going to connect the two sets of dots separately, right? We're not crossing the asymptotes. So for example 1, we have f of x equals negative 4 over x plus 2 minus 1. So the vertical asymptote is whatever makes the bottom undefined, right? It's x equals, and this was a plus 2, so we know its opposite, minus 2. So I know on my graph at negative 2 on the x-axis, I'm going to have one of my asymptotes. And I recommend drawing them as dashed lines. It just gets very confusing with the axes if you try to draw these solid, because then it gets confused with the actual axes. So if you're drawing it dashed, it stands out a little more as that's not the axis. The horizontal asymptote, we see we have a minus 1 afterwards, so we could say y equals negative 1. So negative 1 horizontally on my graph would have been here. So that means I'm going to put this negative 2 in the middle, and that was undefined, so I don't have to worry about it, but I'm going to pick 3 before it and 3 after it. So bigger numbers than negative 2 would be negative 1, 0, and 1. Smaller would be negative 3, negative 4, and negative 5. And now we just have to plug them in. So if I plug negative 5 in, that's going to be negative 4 over negative 5 plus 2 minus 1. So that's negative 4 over negative 3, which is 4/3 minus 1. So 1 1/3 minus 1 is 1/3. It's also going to be some gross numbers that we're plotting. They're almost always going to be decimals or fractions. It's really nice when they work out otherwise, but then we kind of go off the graph because the numbers get a little big. So it's give and take here. If I try negative 4 over negative 4 plus 2 minus 1. So negative 4 over negative 2 is 2, and 2 minus 1 is 1. And then for negative 3, so negative 4 over negative 3 plus 2 minus 1. So this is negative 4 over negative 1, which is positive 4 minus 1 is 3. I'm going to do the same thing with these. I have negative 4 over negative 1 plus 2 minus 1. So that's negative 4 over positive 1 minus 1. We get negative 5. Negative 4 over 0 plus 2 minus 1. So negative 4 over positive 2 is negative 2 minus 1. I have negative 3. And then negative 4 over 1 plus 2 minus 1. So negative 4 over 3 is negative 4/3 minus 1. So I already have negative 1 1/3 minus another 1. So that's negative 2 1/3. Let's get to graphing. So at x is negative 5, I have positive 1/3. So I'm just going to put my dot close to the x-axis, close to 0. Then I have negative 4, comma 1, and negative 3, comma 1, 2, 3. So to graph these dots, connect these dots, what I typically do is I start to the left of my asymptote. I connect, connect, connect. And then I'm going to get close to the other asymptote without crossing. Now let's do these. At negative 1, we have negative 5. At 0, we have negative 3. And at 1, we have negative 2 1/3. So that's really close to the negative 2, but still a little bit off from it. So again, I'm going to go really close to my asymptote. Connect, connect, connect. And then get really close to my asymptote. So there's one here for you to try. You can pause. The answer is posted in the blank notes on Google Classroom. So here, we're not going to actually graph, we're just going to identify the key info. So there's nothing with the x, so x equals 0. And because that's my h value, I can go straight to domain and say negative infinity to 0 and 0 to infinity. Let's do the horizontal asymptote next. So the horizontal asymptote, I see a negative 2 afterwards, so y equals negative 2, which means I could say negative infinity to negative 2 and negative 2 to infinity. And now for my intercepts. The x-intercept, remember, is when y is 0. So if I were to plug 0 in here, I'm going to solve this equation. So I would add 2. I could multiply both sides by x. And now I could divide both sides by 2. So x is equal to 3/2, or 1.5. So that means 1.5, or 1.5, comma 0 is the x-intercept. The y-intercept, remember, is when x is 0. So now we have y is equal to 3 over 0 minus 2. Now we know that that's not allowed. So that means there is no y-intercept. And this makes sense because think of it this way. The vertical asymptote was the line x equals 0, which is the y-axis. So that means we're never ever crossing the y-axis. So as soon as you have an asymptote of 0, the opposite intercept would not exist. So here's one for you to try. You can pause. Answers are posted in our blank notes on Google Classroom. All right, example 3. We're going to use division to rewrite this equation into the form that we're familiar with, and then we can graph and identify the key info. So we're going to use long division. So what we're dividing by goes on the outside. What we're dividing goes on the inside. So now what would I have to multiply x by to get 3x? We would multiply it by 3. So now I'm going to multiply. 3 times x is 3x. 3 times positive 1 is positive 3. And now we subtract. And when I subtract this, the 3x is canceled out, and 5 minus 3 was 2. So what this would look like is this would be 3 plus the remainder of 2 over what we divided by x plus 1. So the only thing that we would have to change to make it look like this is we'd flip it around. 2 over x plus 1 first, plus 3. So that's my equation. Our key information now. So the vertical asymptote, we have plus 1 on the bottom, so x equals negative 1. And my domain would go negative infinity to negative 1 and negative 1 to infinity. My horizontal asymptote, I have the plus 3 afterwards, so y equals 3, negative infinity to 3, and 3 to infinity. I can graph my two asymptotes. X is negative 1, x is negative 1, and y is positive 3. Okay, x-intercept, so if this was equal to 0, if 0 equaled 2 over x plus 1 plus 3, then negative 3 would be equal to 2 over x plus 1, times that by x plus 1, so negative 3x minus 3 is equal to 2. Add the 3, negative 3x equals 5, and divide, so I get negative 5/3. For the y-intercept, I plug in 2 over 0 plus 1 plus 3. So 2 over 1 is 2, 2 plus 3 is 5. So we have 0, 5. All right. So now for my graphing, we know that we're going to have our vertical asymptote of x equals negative 1 in the middle. That's undefined. So now 3 after it would be 0, 1, and 2. 3 before it would be negative 2, negative 3, and negative 4. And I'm going to save you some of the boring, watch me do the math. So if I plug in negative 4, I get 2 and a third. If I plug in negative 3, I get 2. If I plug in negative 2, I get 1. Plug in 0, I get 5. I plug in 1, I get 4. And I plug in 2, I get 3 and 2/3. So at negative 4, 1, 2 and a third, so a little bit above the 2. Negative 3 is at that 2, and negative 2 is at the 1. Close, connect, 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 close. And then at 0, we have 5. At 1, we have 4, and then we have 3 and 2/3, so almost 4. Get close, connect, 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 get close. So there's one final one for you to try. Same thing, right? We have an equation. You're going to identify the same key information as before. You can pause or end the video here. That is the end of graphing. Oh, I lied. That is not the end. We still have another problem to do. Oh my goodness. So yeah, pause here, give it a try. Come back when you've checked your answers in the blank notes on Google Classroom. Look at that, trying to forget our word problem. So the function g of t equals t minus 1 over t measures the percentage of people as a decimal who have already visited a movie theater within this year with respect to time measured in days. The domain of g of t is 1 to 365, right? So there could be 1 day of this year so far up to the 365 days of this year. So the first thing says find g of 300. So that means we're going to plug 300 in for t. So that's going to be 300 minus 1 over 300. So what I'm going to do here is we're going to get 299 over 300. And they said that it was as a decimal. So I'm going to divide this, and I get 0.99 and then a repeating 6. That's it. They just asked for the answer. But now it's interpret the meaning of g of 300 in the context of the problem. So we know that the t-value is the number of days that have happened so far in this year. So we could say at 300 days or after 300 days, at 300 days. And now this was a percentage written as a decimal. So we can consider this, what would be the percentage we would write this as, and that would be 99.6 repeating. So we could say 99.6 repeating percent of people, right, measures the percentage of people have visited a movie theater within this year. And that would be the end of graphing rational functions.